The first law of motion states that every body perseveres in its state of rest, or uniform motion in a right line, unless it is compelled to change that state by forces impressed thereon. First inferred by Galileo, this property was later transformed into axiom by Newton. The law also became known as the law of inertia. Another property of the mass was raised by Kepler, who used for the first time the word inertia in the study of the motion of bodies. For Kepler, inertia is a property of the bodies to resist acceleration. The reasoning behind this argument is this. 1. If a body maintains its state of rest, or uniform rectilinear motion, in the absence of applied forces. 2. If, conversely, a force is needed to change that state of a body, which means acceleration. 3. Then, that body must have the property to resist that change in its inertial state, or acceleration. Otherwise, an applied force of any magnitude would move the body with an infinite acceleration. Acceleration is defined as follows. The rate of change of the momentum of a body. Momentum is equal to the mass multiplied by the velocity of the body. Since the mass is constant, acceleration becomes the rate of change of the velocity vector. The velocity, as a vector, is a quantity that has both magnitude and direction. The magnitude of the velocity of a body is its speed. The acceleration is linear, when only the magnitude of the velocity vector changes. The acceleration is centripetal, when only the direction changes. From his experiments, Galileo inferred that bodies free of any applied forces move in uniform motion in a straight line. This is called inertial motion. These experiments, however, were carried out on a local scale, that is, of a small region of the spherical surface of the Earth. To prove the first law of motion, however, it is needed to prove the property of the inertial resistance to acceleration, because if the bodies tend to remain at rest, or uniform rectilinear motion, and, if a force is needed to change these states, the bodies should manifest resistance to this change, that can be empirically observed. To demonstrate the inertial resistance to acceleration, a body in rectilinear motion interacts with a body at rest, relative to an inertial, non-accelerated observer, the system being free of any external applied forces during the interaction process. The bodies tend to maintain their inertial states, but, when interconnected, their interaction becomes an inertial confrontation, since their inertial states are conflicting. The result is the contradiction of both tendencies. The bodies resist the change of their inertial states, in accordance with Newton's commentary to the definition 3, Book 1, of the Principia. The inertial resistance of each body acts upon the other as a force, causing their acceleration. This demonstrates that all bodies resist acceleration, that is, the change of their inertial states of rest or linear uniform motion. This experiment also demonstrates that the inertial resistance of each body acts upon the other as a force, according to Newton's inference. The driving wheels of a car, driven by its power train, apply a pair of equal and opposite forces, one upon the car, and the other upon the surface of the earth, causing the acceleration of the car, according to the third law of motion. A box is placed on the car, with supposed negligible friction. When the car moves, accelerating, the box is not accelerated, because no driving force is acting upon a car, and a support wheel base, are acted upon by equal and opposite driving forces, applied by the driving wheels of the car. Now, the car is connected to a wheeled box, by an unstretched spring. When the car and the wheeled base accelerate, they manifest resistance to acceleration, as required by the first law of motion. The spring starts to be stretched by the driving force. The driving force acts upon the wheeled box, through the spring, causing the acceleration of the box. The box then resists acceleration. The resistance of the box to acceleration acts upon the car. The sum of the resistances of the car and the box to the forward acceleration equals the resistance of the wheelbase to the backward acceleration, as required by Newton's third law. The second law of motion is the way to calculate the acceleration of a body, with a given mass, acted upon by a force with a given magnitude. The second law is inside the third law of motion, and simplifies the calculation process. But, its isolated use leads many people to think that the third law is merely a redundancy. Almost everybody knows that the acceleration of a body acted upon by a force is calculated using the second law. And, to that acceleration, in a given direction, the action shall correspond a simultaneous acceleration of another body, in the opposite direction, the reaction. But, how are action and reaction related to each other? It is very common, when we consider the acceleration process using only the second law, to ignore the required opposite acceleration, as if the applied force was a self-force. The problem is that, when a body is acted upon by a force, the body resists. This means that, the driving force must be produced by a force provider, which requires a support body to act upon. This is because the second body, B, also resists the action of the opposite force produced by the force provider, allowing the second body to act as a support for the acceleration of the first body, A. This results in the opposite accelerations of the two bodies, that act as a support for each other. These are the conditions, provided by the third law of motion, to allow the acceleration of the bodies. In certain circumstances, it is possible to feel the inertial resistance to acceleration, as when an elastic part of a structure is accelerated, against a body not rigidly attached to that structure. As first inferred by Kepler, if the bodies did not resist acceleration, they would move with infinite acceleration, when acted upon by any force. Therefore, the relation provided by the second law would be impossible. While the third law of motion establishes the conditions to obtain the acceleration of bodies, the second law allows the calculation of the three components of the process, that is, the force, the mass and the resulting acceleration, by means of their relation. This is the reason why the second law has become the key element to the mathematical development of the classical mechanics. But the third law should always be taken into account to consider the conditions for any acceleration process. In other words, the third law reflects the condition of symmetry for any acceleration process in applied mechanics. The previous arguments also apply to the problem of impact. When a body with a given mass, m, is in motion with a given velocity, v, relative to a non-accelerated, or inertial observer, it has momentum, that is, its mass multiplied by its velocity, mv. When the body collides with another body, supposed at rest, with respect to that non-accelerated, or inertial observer, an inertial confrontation occurs, because their inertial states are conflicting. The moving body tends to remain moving, and the body at rest tends to remain at rest. The bodies resist the change of their inertial states, and their resistances act upon each other. The result is the contradiction of both states, and momentum is transferred from the moving body to the body at rest. An interesting and special case occurs when the mass of the two bodies are equal. In the interaction process, the momentum of the moving body is totally transferred to the body initially at rest, given the condition of the elastic impact. One message of this video, for those who are not fully aware, is to highlight the mathematical importance of the second law, but its inability to completely state the necessary conditions for the acceleration of bodies in general. These conditions can only be fully understood, taking into account the details inscribed in the third law of motion. Applications. Starting with the third law, the acceleration processes that underlie our motion technology can be divided into two main groups: the linear and the curvilinear processes. The linear processes can also be divided into two groups, depending on how a basic form of energy, thermal, chemical, nuclear, etc., is transformed into kinetic energy in the bodies, or transferred directly as kinetic energy from one body to another. In the first case, a primary form of energy is transformed into kinetic energy in the bodies, by means of an appropriate process inside the force provider. A wide-used energy transformation process is the combustion in a chamber. In the second process, kinetic energy, produced in the first case, is transferred from a body with a given momentum, to another body, through a process of impact. In all thermal processes, both types of linear processes are employed. For example, in the rocket, kinetic energy is initially produced in the combustion process, and, then, the huge number of impacts of hot, high-speed gas molecules, against the combustion chamber wall, opposite to the exit nozzle, is transferred to the rocket body. Of course, the net result of the impacts of the gas molecules on the walls is pressure. It should be remembered that the thrust associated to the rocket acceleration is not calculated using the differences of pressure, since the mass of the rocket is variable. The same process occurs in the internal combustion engine, when, in the combustion process, chemical energy is transformed into kinetic energy in the hot, high-speed gas molecules that collide with the wall in the piston head, that appears as internal pressure. The colliding gas molecules transfer momentum to the piston, that is converted into torque in the crankshaft. Another application of Newton's third law linear, is the electromagnetic levitating train, that uses the principle of the linear electric motor, to obtain the acceleration of the train on a trail, fixed on the surface of the Earth. In this case, electric energy is converted into kinetic energy, in the train and the ground. Of course, due to its huge mass, the displacement of the Earth is unmeasurable. The second group of acceleration processes is the curvilinear. This is a kinetic energy transfer process, that uses the inertial resistance of a moving body, in a straight path, to the incurvation of its path. A body gains kinetic energy in a process of energy transformation, that can be thermal, as in the case of gas turbines, or the kinetic energy gained by a water mass flow, that falls from a certain height, as in the case of water turbines. A moving body interacts with another body, and resists the incurvation of its path, a centripetal acceleration, which results in momentum transfer, from the moving body to the body causing the incurvation of its path. This is the same kind of interaction by inertial confrontation, that occurs between a car and a curved section of a highway, attached to the surface of the Earth. The car, moving in a straight path, is constrained by the curved structure. The car resists the incurvation. This resistance acts upon the Earth, as a centripetal resistance. The resistance of the Earth, the ground, acts upon the car as a centripetal force. This is the way by which Newton's third law is obeyed, as detailed in other videos. The same mechanism is employed in the case, for example, of steam or water turbines. A water mass flowing in a straight path interacts with the turbine blade, and then an inertial confrontation occurs. To continue in its rectilinear motion, the mass flow has to move the blade, and cause the rotation of the turbine with a corresponding angular speed. The resistance of the turbine to acceleration acts upon the mass flow, to maintain its initial state of rest, relative to the inertial observer, causing the unilateral incurvation of the flow, that should follow the blade face curvature profile. The known result of this inertial confrontation process, is the contradiction of the inertial tendencies of the two bodies. The curved path followed by the mass flow, is intermediary between the curvature of the blade profile, and its initial straight path. In the process, the mass flow transfers momentum to the blade, and, ultimately, to the turbine assembly. One example of a machine using this process, shown here, is the Pelton turbine. The water mass flow has its path sequentially incurvated by the turbine buckets. The velocity of the water leaving the bucket is lower than the velocity in the incoming flow. The difference between the two velocities multiplied by the mass of water moving in the bucket is the amount of momentum transferred to the turbine assembly in that small time interval that becomes torque on the turbine shaft, to be used, in general, to drive an electric generator. In this case, the gravitational energy of the water mass flow is transformed into kinetic energy in the jet, which is, ultimately, converted into electric energy in the generator, through the turbine. In other words, the turbine extracts energy from the water flow, by means of the process of incurvation of its path.